Good morning, everyone, and welcome to our first webcast in our three-part series, Critical Safety Tips on Short Circuit Current Rating, or Sccr, for industrial control panels and industrial machinery. In these webcasts, experts from both Eaton's Busman Series team and UL take a closer look at important topics around Sccr. My name is Shannon Stokes with the Busman team, and I'll be your moderator for today's webcast. Today's webcast is on determining Sccr of industrial control panels per the third edition of UL 508A. Our speakers are John Kovacic with UL and Dan Neeser with Busman. Before we get started, I'd like to mention a few housekeeping items. First and foremost, please mute your phones. We will place everyone on mute to ensure good call quality, but it improves if you mute yourself as well. If during this webcast you have a question, please send that question via the chat function. We'll address these questions at the end of the webcast during our Q&A session and follow up with any unanswered questions. I'd like to repeat, please mute your phones now. This webcast is being recorded and an on-demand link will be provided to all attendees following this broadcast. One final item, please do not put your phone on hold during this webcast, as that hold music is disruptive to the webcast. I'd like to introduce Dan Neeser, Senior Field Application Engineer for Eaton's Busman Series Solutions. For more than 25 years, Dan has been providing technical guidance to consulting engineers, OEMs, electrical contractors, and industrial and electrical inspectors. He is sought after for his training expertise, particularly around Sccr. He participates in IEEE, NEMA, NFPA, UL, and IAEI panels and activities. I'd also like to introduce John Kovacic, Primary Designated Engineer at UL for industrial control equipment, components, and assemblies, including control panels and industrial machinery. His 45-year tenure with UL has covered countless codes and standards and technical committees. He sits on NEC and NFPA committees and serves as technical advisor for the IEC. Today's webcast will cover three topics. First, industrial control panels and industrial machinery. Second, UL 508A standard for safety industrial control panels. And third, determining overall panel Sccr. I'll now turn it over to Dan.
Thanks, Shannon. The first thing we're going to talk about today is industrial control panels and industrial machinery as it pertains to the NEC. And I'll start with industrial control panels. So quite simply, an industrial control panel is an assembly of two or more components. So it's simply a piece of electrical equipment that has two or more components that can't be classified as another type of equipment. So for instance, it's not a panel board, it's not a switchboard, but it is electrical equipment, and therefore it falls in this general category called industrial control panels. The panel might contain power circuit components, things that perhaps supply power to loads, as we'll see. It might contain control circuit components, or more likely, it probably contains a mixture of both power and control. And very importantly, the industrial control panel does not include the controlled equipment, and John will talk about what that type of equipment is called in his slides. So there are three main considerations when it comes to the NEC requirements for industrial control panels. The first is that the industrial control panel must be marked with the Sccr, and that must be plainly visible. Now there's some discussion on what that means, but in general, in the eyes of UL today, the standard at least, UL 508A, that requires the Sccr marking to be on the exterior of the machine. Of the industrial control panel. 409.22b is new in the 2017 NEC, and that requires the user to determine the available short circuit current, or what we might call the fault current. The available fault current in the 2020 code is referred to, and then provide date and documentation to the AHJ of that information. And then most importantly, 409.22a instructs the user not to install the equipment if the Sccr is less than the available short circuit current. And now I'll pass it to John for industrial machinery.
Thanks, Dan. Good morning, good afternoon, ladies and gentlemen, wherever you are. It's a pleasure for me to be part of this webinar presentation. Dan has been talking about Article 409 of the National Electrical Code and the requirements for industrial control panels. Let's spend a few minutes on short circuit requirements for industrial machinery. Those requirements are also contained in the National Electrical Code. Machinery is covered in Article 670 of the NEC. First, let's look at Section 670.2, which contains a definition for industrial machinery. You see, it's a power-driven machine or group of machines working together in a coordinated manner, not portable by hand. Not portable by hand is a key point. There's a lot of tools and different types of machinery that are considered outside the scope of NEC 670 and also outside the scope of NFPA 79, which is the electrical standard for industrial machinery. I won't read through the rest of the definition, but you can see it's quite extensive, and it's intended to cover many, many different types of assemblies that are considered to be industrial machinery and falling within the scope of Article 670. Keep in mind that the NEC covers the installation of the machine to the source of supply, and that also could include the conductors to the machine, the sizing of those, and the overcurrent protection for the machine, and the sizing and the selection of the protection as well, and the need for a disconnecting means to isolate the machine from a source of supply. While NFPA 79 covers all of the equipment downstream from the point of connection where the machine is electrically connected to the source of supply. But on the NEC side, there are requirements that cover the need for a short circuit current rating. And let's look at those. You can see that the requirements in NEC, which are related to short circuit, are shown on this slide. For example, in 670.3 (A)(4), we see that short circuit current rating must be marked on the nameplate and plainly visible, very similar to the requirement in Article 409 for control panels. We see in 670.5 (2), there must be a field marking with the maximum available short circuit current. This is new for the 2017 edition of the code. And you can see in your lower right-hand corner of the slide, there's a typical nameplate that would be put on in the field, and this would be the field marking I'm speaking of required in 670.5 (2). You can see that the marking includes not only the available fault current, the supply voltage, but also the date on which the calculation has been performed. That's also a requirement in the NEC. It's very important to identify the short circuit current available at the time that the marking was applied, because there's a good chance that in the future sometime the available current could increase. The utility could provide a larger transformer outside the building supplying this machine, and a number of other things could happen to the electrical distribution system in the building where the machine is located. So providing the date is very important. And then lastly, we can see at 670.5 (1), there's a very important statement. Do not install where the short circuit current rating is less than the available short circuit current. This is a key point. This is really the reason for calculating and determining a short circuit current rating for equipment, because when the equipment is installed in the field, that rating has to be able to be at least equivalent to the available fault current at the point where the machine or the control panel is connected. If that rating is less than the available fault current, there's no guarantee that the machine or the control panel will be safe if a fault occurs. You could have different kinds of damage due to a fault, and that damage could cause injury to people, damage to property. So making sure that the short circuit current rating is at least equivalent to the available fault current is very important. So how do you determine the short circuit current rating for equipment? Well, whether it's a panel or a complete machine, as we discussed, there are basically two ways to determine equipment short circuit current ratings. The first way is by doing testing of the equipment. And this is very common for components. And of course, in these panels, whether they're by themselves or part of machinery, they contain many different components that need to have short circuit current ratings, and in particular those components in power circuits. So the easiest way to establish short circuit current ratings for components is to do testing and evaluate the product under short circuit conditions to the requirements in the component standard. And there are many UL product standards that cover the components I'm speaking of. The second way to determine the short circuit current rating of equipment is by what we call an analysis method. This is for a device or apparatus and assembly. And the best example of an analysis method is in UL 508A, the standard for industrial control panels, and specifically supplement SB of the standard. This part of the standard contains the requirements for determining the short circuit current rating of a panel, and it's what I would say probably the most popular analysis method, and it's recognized in the National Electrical Code, specifically in Article 409 in an informational note where the standard is called out, specifically referencing supplement SB as a typical method for determining the short circuit current rating of equipment. So if you look at these two methods, you can easily see that short circuit testing is really limited to manufacturers of components and manufacturers who have the ability to perform tests in their own laboratories or be able to rent laboratories, incur the cost of doing all the testing, which is quite expensive. So for most companies building assemblies, like UL panel shops, for example, they're going to rely upon the analysis method because that is a method that allows you to determine the short circuit current rating without having to perform any tests. It's based on the use of components that have been previously tested and have established short circuit current ratings. So in part 2 of this webinar, we will examine and discuss some important terminology in the UL 508A standard that will lay the groundwork for the process of determining a short circuit current rating for equipment. That's a good segue into the next segment of our webinar, and for this, I'll turn it back over to Dan.
Thanks, John. And again, I'd like to add the importance of having the proper Sccr when it comes to either industrial control panels and industrial machinery. Many of our attendees, I'm sure, have seen equipment that comes with a label of 5 kA or 5,000 amp rated Sccr. And I think what your users will find is that quite simply 5 kA is not adequate for most commercial and industrial installations. And that's why we're doing this webcast, is to really explain to the to our users here what can be done to get equipment that is rated properly for their available fault current at their system. Before we get into the requirements of UL 508A supplement SB and determining the Sccr of an assembly, it's very important to start with the definition. So I'm going to cover the key definitions that will pertain later in the presentation when it comes to analyzing your panel for Sccr. And the first thing, we kind of talked about this before, is that we have power circuits and we have control circuits. And when it comes to Sccr, only the power circuit devices affect the assembly Sccr. We don't worry about the control circuit components. And if you look at the definition in UL 508A, a power circuit is simply the conductors and components of branch and feeder circuits. And to understand that, we're going to have to actually go to a definition of branch and feeder, which we will do in just a second here. What's not a power circuit? That would be control. So something that carries the electrical signals directing the performance of a controller, but does not carry the mainline power. And in most cases, the control circuit is limited to 15 amps. There are some exceptions to devices that do not have an Sccr. Things such as transformers, for instance, dry type capacitors, one-port SPDs, wide delta contactors, cord and plug connected enclosure ACs, wiring ferrules, and filters when used with power conversion equipment. So let's understand what power circuit means more. And we said before that it was a part of a branch or feeder circuit. And a branch circuit is defined as the conductors and components following the last overcurrent protective device protecting a load. And that really is the key word that I stress with my industrial control panel manufacturers, is when it comes to determining power versus control, the key word there is load. So the question we should ask is, well, not what the voltage is. So for instance, it might be a 120 volt. A 120 volt circuit could be either power or control. It just depends if it supplies a load. And in general, a load is considered, and I should mention it's an external load, are considered motors, lighting, heating, appliances, and convenience receptacles. If a receptacle is marked programming only and load limited, it is not considered a branch circuit. Let's also understand the definition of power transformer versus control transformer. A power transformer is simply a transformer that supplies a load. And when we have a power transformer, we will need to analyze the secondary components on the transformer for Sccr. If we have a control transformer that only supplies control circuits, then we would stop at the primary overcurrent protective device interrupting rating. This is just an example that kind of explains both the branch versus the feeder. And I should mention, I forgot to cover what a feeder circuit is, but a feeder circuit is quite simply anything ahead of the branch circuit. So we start from our load. As you can see, we have 4 motors in this example here. We go up till we hit the first branch overcurrent device, and by definition, that is where the branch circuit starts. Anything on the line side of that is classified as a feeder. And the reason we say this is there are important rules where certain devices in the feeder can affect devices in the branch. And so we have to understand what a branch and a feeder is, and this illustrates what that is. There is another device that we have to worry about, and those are devices that perhaps supply a control circuit. Those devices will affect it, and I mentioned this earlier, the primary device, for instance, of a control transformer, that will affect the Sccr. So if you can see in the example here, in the example shown on the screen here, we tap off the feeder circuit and we go to a control transformer protected by 2 fuses. Those fuses must be a branch circuit overcurrent device, so meaning that they must be a class fuse if I'm using a fuse for overcurrent protection, and that would affect the Sccr. In some cases, we might tap off of the load side of the branch circuit overcurrent device and create a single control circuit for a given single branch circuit. In those cases, the branch circuit device can be either branch circuit, the overcurrent device can either be branch circuit or it can be supplemental protection, but in either case, it does affect the assembly Sccr. And there's also an exception noting that if we do supply a power supply, provided it's 100 VA or less with a 24 volt maximum secondary, then that is also control power. And now I'm handing off to John Kovacic to talk about what method for determining the overall panel Sccr.
Well, thank you, Dan. A lot of good information there you've shared with our attendees. In this next segment of the webinar, we're going to talk about determining the overall panel short circuit current rating. Let's begin by looking at the steps in the process to determine the short circuit current rating. You see we have 4 bullets, and let's just take a look at each one individually. The first one, determine the short circuit current rating of each branch circuit. As you see in the picture alongside the bullets, we have a panel that what looks like 3 individual branch circuits. So you have to look at each one individually because each one will have its own short circuit current rating, and that'll be dependent on the short circuit current rating of the components in the branch. For example, a contactor or an overload relay, or you could have a variable frequency drive. And then, of course, what's important is the overcurrent protection, the branch circuit overcurrent protection in each of those circuits. All of those components affect the overall short circuit current rating of each branch. So that's the first step in the process. Next, we want to determine the short circuit current rating for each feeder component. So we see, again, in our example, that we have one feeder circuit supplying 3 branches. And in that feeder circuit, we have what looks like a circuit breaker, or it could be a fuse disconnect switch. But that particular device in the feeder circuit is very important because it has to have a short circuit current rating or an interrupting rating to support the overall rating of the industrial control panel. The third bullet, identifying the interrupting rating for each overcurrent protective device. That's very important. We see we've got 3 overcurrent protective devices in the branch circuits because we have 3 branch circuits, and then we have an overcurrent protecting device in the feeder circuit. So total for this panel, we have 4 overcurrent protective devices. And there is a requirement in Supplement SB 508A that all overcurrent protective devices, branch circuit overcurrent protective devices in the feeder and branch circuits in a panel, have to have an interrupting rating at least equivalent to the overall short circuit current rating of the panel. There is one exception, and that's when you use a transformer to increase the short circuit current rating of specific components. But we'll talk about that a little later. But the basic rule is that all of the overcurrent protective devices, the branch circuit protective devices, have to have an interrupting rating at least equivalent to the overall short circuit current rating of the panel. And then finally, the last bullet, the panel short circuit current rating is the lowest value of all of the short circuit current ratings that we determine in the above three bullets. It's called the weakest link method, the weakest link. In other words, the short circuit current rating of the panel is going to be based on the lowest short circuit current rating of any component essentially in the power circuits, in the branch or feeder. That's the weakest link method. And of course, Dan pointed out many times, you end up with 5 kA because all it takes is just one component that has a very low rating, like a 5 kA rating, and now you've limited the panel to a 5 kA rating, where the panel may have interrupting devices that have 100 kA ratings. It's unfortunate, but that's what the process basically comes to, or that's what you calculate when you use the requirements in Supplement SB. Well, each of these steps has its own complexity, and if not executed properly, certainly you can see it's easy to make a mistake and calculate an incorrect rating for the panel. Now let's look at the first step in calculating the overall panel short circuit current rating and determine how we complete that part of the process. You can see on this slide we've highlighted a very important requirement in UL 508 Supplement SB, specifically SB 4.2.2, where it speaks of the short circuit current rating of a feeder or branch circuit shall be established by one of the following methods. So this is how we actually determine the short circuit current rating of a branch or feeder. Subparagraph A, the short circuit current rating marked on the component or instructions provided on the component. Sometimes it's difficult to determine the short circuit current rating of a particular component because it's just not available. It's either not marked on the product, or it's not on any instruction sheets or any other information that ship with the product or available for inspection. Subparagraph B, the short circuit current rating determined by the voltage rating of the component and the assumed short circuit current rating from table SB 4.1. So if you cannot determine the short circuit current rating of a component, if you cannot find it marked on the product or any instructions provided with the product, then we have a solution. We have table SB 4.1, and that is a table that provides what we call default or assumed short circuit current ratings. And those are ratings that have been based on historical testing of components and anticipated ratings for components in particular applications. These are assumed ratings, and it's important to point out those ratings only apply when the component is used in the panel. Those ratings cannot be used in other applications, and those ratings cannot be used to, identify a specific short circuit rating for a component. It's not a rating for the component itself. It's only an assumed rating for the component when it's used in an industrial control panel. And then finally, we have paragraph C, the short circuit current rating for a component that has been investigated in accordance with the performance requirements, including short circuit testing for standard fault currents and high fault currents. That's specified in the associated product standard and described in the manufacturer's procedure. The manufacturer's procedure is basically the UL certification report that details all the information about the certification of the product, which would include an area that would identify standard fault current ratings and high fault current ratings and how those were established. So let's expand our discussion of component short circuit current ratings and examine how these ratings are determined for individual components. First, we see there's a minimum rating for a component when testing with an overcurrent protective device. This is what's called the standard fault rating. This is a requirement. It's mandatory for most products in a power circuit, and the mandatory requirement would be in a component standard. Like, for example, we have standard UL 508 for industrial control equipment, and it requires short circuit current ratings and markings to be established for motor controllers. So that would be what we'd call a standard fault rating, and that is mandatory. It's found on the product label, instruction sheet, or it could be determined from a UL website. As I said in the previous slide, if you can't determine this rating, then you use what's called the default rating, which is provided in Table SB 4.1, which is seen on the right-hand side of the slide. This table can be used if it's absolutely impossible to determine the short circuit current rating for a particular component. And then finally, I can't emphasize enough that the default rating only applies when the component is used in a panel. Quite often I get questions about these ratings, and can I apply those ratings on other applications, or can I assume that the product has this rating as an individual component? And the answer is no. So we have identified two types of short circuit current ratings for components. We've talked about standard fault ratings here, and high fault was mentioned in the previous slide. So let's take a closer look at standard fault ratings and how they are determined. And for this, I'll turn it back over to Dan.
Thanks, John. I wanted to commend UL. UL does great classes on UL 508A and Supplement SB. And I remember going back to the standard rating. When I took a class years ago, the instructor said, when in doubt, 5K it out. And I think, unfortunately, that's what a lot of industrial control panel manufacturers do. In many cases, perhaps they don't get the information from their user on what their available fault current is, and if they don't know, they just put 5K on it and out the door it goes. And again, that's primarily based upon the fact that if you look at the standard fault current table, and as you can see here on the label, the basic fault current for a motor controller is 5 kA, 50 horsepower or less. So it's always very safe for them to just put 5 kA on it and not be less than that. So, but again, I want to stress the importance that 5 kA, unfortunately, is typically not high enough for most commercial and industrial installations. So we really need to rely on using components that will have high fault ratings as well as standard ratings. And here we see an example of a high fault rating. So for instance, this motor controller, if the basic rating is only 5 kA with a maximum 45 amp fuse or a 35 amp circuit breaker. However, if you want to apply it at a high fault, we have a high fault rating at 480 volts of 100 kA, provided we have a 20 amp class J fuse or less. If we want to increase that voltage to 600 volts, we would have a rating of 30 kA at 25 amps. And again, that should say really 25 amp class J. Whenever you specify a fuse, you have to specify the class of fuse, because the class can determine the current limiting nature or ability of the fuse. Class J fuses happen to be much more current limiting than class R fuses, for instance. And now I'll pass it back, I think, to John.
Well, thank you, Dan. We're going to talk about the short circuit current of individual power circuit components. And you can see that there is a basic requirement that a product, when it has a short circuit current rating, for example, a standard fault rating, that is supported by a specific protective device. So, for example, a 5 kA rating must be supported by a fuse or circuit breaker that has obviously a 5 kA interrupting rating, and typically that fuse or circuit breaker would be specified because it was part of a test, a short circuit test, to determine that fuse or circuit breaker properly protected the component. You do that for standard fault ratings and high fault ratings as well. High fault ratings, of course, are optional, and so there are many different kinds of protective devices that can be used to establish a high fault rating. The testing is somewhat similar to establishing a standard fault rating, but obviously you need to use a current limiting fuse or circuit breaker to achieve the higher fault current ratings, because you need a protective device that is very fast acting. And of course, when we talk about fast acting, then we get into looking at what we call peak current let through, which is I squared T energy, and I sub P, which is the peak current under short circuit conditions, the peak current of the interrupting device. So the basic requirement is that a product shall be used as a short circuit current rating of a component when the specified branch circuit protective device is provided, and in this case in the panel. Now, we do have some exceptions to this. Obviously, the exceptions are intended to allow substitution of that protective device that is being used to support the short circuit current rating of a panel. Exception number one, we talk about a fuse. that has equal or less than peak let-through current than the fuse or circuit breaker specified for the rating of the component. When we talk about the peak let-through current, we're talking about values that are specified in table SB 4.2 in the standard. That gives you what we call the umbrella values of fuses. And you use that table to determine if you could substitute a fuse for the specified protective device. Exception number 2 speaks to the ability of installing the specified branch circuit protection in the field. There are many panel shops that build panels for customers where the customer will provide the protective device, whether it's branch circuit or feeder protective device. So that allows you to ship the panel out without the protective device that's needed to support the short circuit current rating, but the panel would then be marked to ensure that that specific protective device is provided in the field. Exception number 3 deals with current limiting breakers. Again, that's very similar to the process that you would go through to substitute a fuse for the specified protective device. But in the case of breakers, you need to look at the specified breaker curves for the manufacturer of the breaker to determine the peak let-through, the I²T, and the peak current. And then finally, we have a 4th exception. A current limiting fuse can be permitted to be substituted for a non-current limiting over current protective device. That non-current limiting over current protective device would again be the one that's specified in the marking to support the short circuit current rating for the component. But you could substitute a current limiting fuse provided that fuse has the ampacity and interrupting rating such that it's equal to or greater than the specified overcurrent protective device. Both the ampacity, the continuous current rating of that current limiting fuse, and the interrupting rating have to be equal to or greater than the specified overcurrent protective device. So building on our discussion of high fault short circuit current ratings, let's use this information to determine the short circuit current rating of each branch circuit in a panel. Now, I previously talked about the process of doing this, but let's again emphasize. You need to identify the component short circuit current ratings of each branch circuit device, and that will then determine the individual branch circuit short circuit current ratings. Now, as Dan mentioned, in many cases, what you end up with for a panel is an overall rating of 5 kA. And for many panel shops and their customers, this is just not satisfactory and not suitable for the application. So we need to raise the rating of a panel when it has a very low short circuit current rating. And there are ways of doing this, and the most common one is to provide components in the feeder circuit. Components, for example, that consist of a current limiting fuse or circuit breaker. And when you specify those components, the objective is to have those components raise the short circuit current rating of the individual branch circuits. So you need to determine if the branch circuit SCR can be raised by using the feeder components. And raising the branch circuit current using current limitation is a very important tactic used by panel manufacturers to increase the overall rating of the panel to meet customer and application needs. And I'll turn it back over to Dan to get us started on discussing this very important tactic.
Thanks, John. Well, basically, as mentioned, there are basically 3 ways to raise components in the branch circuit using devices in the feeder circuit. So essentially here we have, for instance, we have 3 contactors, and perhaps we've identified that those contactors have an Sccr of a given value, and we want to raise that. Now I do want to mention that, and I kind of alluded to this earlier, in many cases if I'm using 5 kA components, using a current limiting over current device might be very difficult to raise that 5 kA rating. So in many cases where we're using a current limiting breaker or perhaps a current limiting fuse, we're going to have a component with at least some level of a high fault rating. Now when it comes to the third option, which is a power transfer, that might be where perhaps we can raise those 5 kA components. So we have 3 basic options. We can use a transformer, and again it'd be a power transfer because it must be in the feeder circuit. Okay, we can use a current limiting circuit breaker and a current limiting fuse. And if we do use a current limiting circuit breaker or a current limiting fuse, we are allowed to have that supplied outside of the panel. if provided we field mark that. And we'll discuss that a little bit more in detail here coming up. But again, I want to highlight that the fact is, if you want to raise low rated components like 5 kA components, you're probably best to turn to your power transformer and use that method. And I'll turn it back to John as he discusses the method of use.
Thanks, Dan. As Dan was just saying, we've got one method to increase the short circuit current rating of a panel. That's to use current limiting components in the feeder circuit. But there is another method, and that's using a power transformer. So let's examine how a power transformer can be used to increase the short circuit current rating of a branch circuit and ultimately the overall short circuit current rating of a panel. Now, you can see on this slide that we have a panel that has a power circuit supplied by a transformer. So now this becomes a power circuit transformer. It has primary overcurrent protection, and then the secondary of the transformer is basically providing the branch circuit. It's a source for the branch circuit, which consists of the branch circuit overcurrent protective device, the components in the branch circuit, and then the external load. So the SCCR of this branch circuit that's connected to the secondary can take on the interrupting rating of the primary side overcurrent protection. The primary side overcurrent protection if the component short circuit current ratings and the interrupting ratings of the devices in that branch circuit connected to the secondary are equal to or greater than the secondary short circuit current calculated or defined in table SB 4.3, which would be for single-phase transformers, and then table SB 4.4 for three-phase transformers. So what we're doing here is using a transformer as a limiting impedance so that it limits the amount of short circuit current available to the branch that's connected to the secondary. So the objective here is to select a transformer that limits the current to a value less than the individual short circuit current ratings of the components in the branch. So then the lowest short circuit current rating or interrupting of any of the downstream devices is the secondary short circuit current, which is greater than any of the downstream component short circuit current ratings or interrupting ratings. So we can see that once we determine what the rating of the branch is, if the overall branch is rated more than, equal to, or greater than the available short circuit current from the transformer secondary, now that entire circuit, that transformer, everything downstream, has a short circuit current rating which is equivalent to the interrupting rating on the primary of the transformer. So if the primary of the transformer, for example, has class CC fuses that have 100 kA interrupting rating, now that entire circuit shown on the right side of the slide takes on a short circuit current rating of 100 kA. So let's look at a typical example of how a power transformer can be properly selected to increase the short circuit current rating of all the components connected to the secondary winding of the transformer. You see here that we have a single phase transformer. It's rated 3 kVA with a 120 volt secondary. We go to table SB 4.3, which, as I mentioned, is as supplement SB of the standard, and we can determine from the table that this particular transformer has a available short circuit current in the secondary of 1,200 amperes. That's the maximum short circuit that can be delivered to the components connected to the secondary of this transformer. So now we looked at the downstream overcurrent protective device interrupting rating, and we look at the component short circuit current ratings, and we see that what looks like a circuit breaker has an interrupting rating of 10 kA, and then we have a contactor connected to the load side of the breaker, which has a short circuit current rating of 5 kA. So we see that these products can now be protected because they have ratings, either interrupting rating or short circuit current rating, greater than the available fault current that can be delivered by the secondary of the transformer, which in this example is 1,200 amps. So what happens then, we look at the primary side overcurrent protective device of the transformer. It has fuses that are rated 200 kA interrupting capability. So now the entire circuit that's shown on the right-hand side, that entire circuit that's covered with a dotted line, a dashed line, that now has the short circuit current rating of 200 kA. So you can see that using fuses in a feeder circuit is an excellent means of increasing the short circuit current rating of all branch circuits supplied by a feeder. And I'll turn this back over to Dan to show you how this is accomplished.
Thanks, John. And for those users who have perhaps used the UL 508A standard, they might realize that that table is new, actually, or newer to the standard. Before, there were just rules for either 5 kVA or 10 kVA transformers, and by adding these tables or equations, we now improve the flexibility of using a transformer to raise low ratings. And as I want to point out here, as John mentioned, the key thing here is a transformer can raise both the interrupting rating of an overcurrent device as well as the component Sccr. Now, when we go to current limiting overcurrent devices, this is where the big differentiation comes in. A current limiting overcurrent device, whether it's a current limiting fuse or a current limiting breaker, is only allowed to raise the branch component Sccr. Okay, it is not allowed to raise the branch interrupting rating overcurrent device rating, or if it's a combination motor controller, it cannot raise that Sccr. So when it comes to the let-through of a current limiting fuse or a current limiting circuit breaker, we're only addressing correcting the component Sccr, and that's the biggest difference between a transformer and a fuse. The other issue is, and I'm just going to show you an example using a current limiting fuse. You certainly could use a current limiting breaker as well. When we use a current limiting breaker, as John mentioned before, we would use actual published manufacturer data. So we would contact the manufacturer of the current limiting circuit breaker and ask him for a current limiting chart that shows him the peak let through and the I2T let through at a given available short circuit current. When it comes to fuses, we can't take that advantage. Now, manufacturers of fuses do publish actual let through curves for their fuse, but we want to be using a conservative approach to this, and as such, we use the peak let through current and the I2T from the table SB 4.2, and that shows values of peak let through and I2T that all manufacturers must meet for a given class and ampacity of fuse. The overall process is we're going to identify what the let through current is of the current limiting fuse or current limiting circuit breaker, and then compare that to the component Sccr. And if we can raise the component Sccr, we will raise that device. So I mentioned earlier table SB 4.2. This is a table that identifies the peak let through and the I2T of the current limiting fuse. Now, many people might ask, well, why are we using the peak let through rather than the RMS let through? And the reason is quite simply that we don't document the RMS let through, whether it's a current limiting breaker or a current limiting fuse. We only document the peak let through. If we did document the RMS let through in a table like this, we would be able to use that. Unfortunately, we do not. So essentially, we're using a much more conservative level of let through current in this analysis. So what we would do is we would then identify, in this case, we have the table for class CF fuses up to 400 amps and J and T fuses 600 volts. So all those fuses have the exact same requirements for fuse let through. And as you can see, there are 3 levels of testing we do. We do testing at a fault current of 50 Ka, 100 Ka, and 200 Ka. And the key here is to find the corresponding peak let through for a given class and ampacity of a fuse at a given fault current. So what I've done here is a simple example here. And as I mentioned before, you're not going to be using typically a current limiting fuse to raise a 5 Ka component, because often your feeder overcurrent device is way too large in ampacity to get that 5 Ka let through. So for instance, from a chart, if you look at the class CF, J, and T fuses, if I wanted to have a let through at 100 Ka of 5 Ka, I'd have to limit that to a 20 amp fuse. So again, it's very difficult to get a current limiting fuse to raise a 5 Ka component, hence why we have the transformer rules. However, what you can see here is we have a combination of a 14 Ka circuit breaker and a 22 Ka contactor, and again, the only thing we'll be addressing in this circuit is the 22 Ka contactor, okay? And this has a Sccr of 22 Ka. So if we had an overcurrent device, a current limiting fuse in the feeder, and perhaps that was a 200 amp overcurrent device, the let through at 100 Ka, the peak let through, will be 20 Ka. So what we are saying is if there's a fault in that circuit, the worst case peak let through at a fault of 100 Ka will be 20 Ka. As long as 20 is less than 22, which it is, we are able to raise that component to 100 Ka. However, as mentioned earlier, we cannot raise the interrupting rating. So essentially we fixed the component, but we did not fix the overcurrent device rating. So essentially that circuit remains at 14 Ka regardless of the let through of the current limiting fuse. The solution certainly would be to look at a larger overcurrent device. So if our goal was to get higher Sccr, we would look at an overcurrent device that would be able to provide higher interrupting rating. And oftentimes going to a current limiting fuse is the simplest and most economical way to do that. So for instance, we could go from a 14 Ka circuit breaker to a 200 Ka fuse. Perhaps those are class CC fuses with a 200 Ka rating. And what you'll find by changing from a breaker to a current limiting fuse, you also might raise the rating of the contactor. So for instance, that contactor had a 22 Ka rating with the circuit breaker. However, if I have a class CC or J fuse, that rating becomes, the tested rating becomes 100 Ka. So by making the change from the 14 Ka breaker to the class CC fuses, for instance, we've not only raised the problem with the overcurrent device interrupting rating, but we've also raised the rating of the contactor. So right now we have a 100 Ka rating right there. That would be our circuit rating. And if I look at this, there's actually a mistake in the slide here. I should have identified what the overcurrent of what the let through is at 200 Ka. And if we look at the let through of 200 Ka for a 200 amp class J fuse, it actually is 30 Ka. So why I show the circuit as 200 Ka is because if I look at the let through at 200 Ka, the peak let through is 30. 30 is less than 100. I can then raise 100 to 200 Ka. I mentioned earlier that in some cases it's advantageous to have that current limiting overcurrent device be supplied in the field. And that's because we're going to need protection of the conductors coming to the industrial control panel. And oftentimes that overcurrent device that protects the conductors might also be able to provide the high Sccr for the industrial control panel. So what we show here is that current limiting overcurrent device, in this case a current limiting fuse perhaps, could be supplied upstream of the industrial control panel if it's properly marked. And as you can see, we would have an example of a label there that says the Sccr is 100 Ka RMS symmetrical when fed by a maximum 200 amp class J fuse. If we don't have that 200 amp class J or less fuse, then we have to default to 5 Ka. So that really puts the burden on the user of the equipment to supply the proper overcurrent protection to get that high Sccr. And that's acceptable per the UL 508A standard. Why would we want to do this? Well, it's quite obvious. The first thing, from an industrial control panel manufacturer perspective, I have one less component that I have to supply. That reduces my cost. And with one less component, I also can reduce my enclosure size. So both of those are going to provide cost savings to the industrial control panel and ultimately the user of the equipment. The other benefit of that is by having the current limiting device upstream, you likely have a low arc flash hazard with the equipment, okay? And you also will have the case where when I turn that disconnect off outside of the industrial control panel, everything in there is de-energized. That helps improve electrical safety. And with that, I'll turn it back over to John to discuss how we address the feeder circuit components.
Well, thank you, Dan. But let's wrap things up by summarizing the steps in the process to determine the overall short circuit current rating for a panel that incorporates both feeder and branch circuit components. First, we need to determine the short circuit current rating of all branch and feeder components. This is basically using the weakest link method. We've talked about this already in the webinar, and we emphasize the importance of being able to identify short circuit current ratings for individual components. But ultimately, the weakest link method will prevail to determine what the individual short circuit current rating is for a branch circuit. Next, we need to identify the interrupting rating for each overcurrent protective device in both the feeder and branch circuits. Remember that the overcurrent protective device needs to have an interrupting rating at least equivalent to the short circuit current rating of the panel. The only exception would be if the overcurrent protective device is on the secondary of a power transformer used to increase the short circuit current rating of an individual branch. But the basic rule is that all the protective devices, the overcurrent protective devices for the branch circuits in the feeder, need to have an interrupting rating at least equivalent to the short circuit current rating of the panel. And then finally we come to our conclusion, which is the overall short circuit current rating of the panel. In this case, we have a rating of 14 kA RMS symmetrical. It's probably a very low rating compared to what the customer needs, but that is what we concluded based on an analysis of each individual branch circuit and feeder, looking at the overcurrent protective devices and their interrupting ratings. And in this case here, we obviously did not use feeder components to raise the overcurrent, the short circuit current rating of the panel, not certainly with the panel rated 14 kA. So as Dan and I have discussed in previous slides, there are methods for increasing the short circuit current rating of a panel. You can use current limiting devices in the feeder circuit, or you can use a power transformer. So this concludes the technical presentation portion of the webinar. I will now turn the program over to our moderator, Shannon, for a Q&A session.
Thank you so much, John. Thank you as well, Dan. We have about 6 minutes left in this webcast, so let's go straight into our questions from the audience. Question number 1, is an industrial control panel required to be listed?
Dan, why don't you take that?
Okay, fantastic. Yeah, that is a great question. If you look in the National Electrical Code, Article 409, or for industrial machinery, Article 670, it does not require either an industrial control panel or industrial machinery to be listed. Now, that being said, I certainly support the enforcement that requires listing of equipment. Again, the NEC is the minimum standard, right? The minimum level. And I often recommend going beyond that. I would love to see a code proposal that would require industrial control panels or industrial machinery to be listed. I believe that would be beneficial. As mentioned earlier, there are some jurisdictions that do require listing of equipment. I happen to handle the Midwest area for the busman division. And if in areas like Minnesota, I also know areas like the West Coast, like Washington, Oregon, I know that they require listing. So it's not required by the NEC, but be careful because it might be required by the local jurisdiction.
Thanks.
Great answer, Dan.
Yes, thank you. Question number 2, what Sccr are you seeing customers request? Is 5 kA usually okay?
I'll take that one, Dan. I think what happens with a lot of customers is they simply do not know what short circuit current rating they need for their panel. They either have not received any information from their customer, or the customer doesn't know what the available short circuit current is at the point where the panel is going to be installed. So this is a common problem with a lot of panel shops, and that's why they just put 5 kA on the panel, because that's the path of least resistance. They don't need to be concerned about adding components, for example, in the feeder circuit to increase the short circuit current rating. But unfortunately, in most cases, that 5 kA rating is not going to be adequate. But it's just a lack of information. It's a lack of understanding. And I will say that to determine the short circuit current rating where the panel is going to be installed can be a challenge. You have to, in many cases, get the utility involved. You have to do a study to determine what the available is at that point in the electrical distribution system for a building or structure where the panel is located. So it can be a challenge, but people have to go the extra mile, because if they really want a safe installation, they really should know what the available current is, the short circuit current at the point where the panels can be installed, so that the panel will have a short circuit current rating that supports its installation there and can be code compliant. The code, certainly, whether you're in Article 409 or 670, it does require the equipment to have a short circuit current rating at least equivalent to the available short circuit current at the point where it's connected.
Thanks, John. Next question, are series ratings allowed to be used in industrial control panels?
Dan, you take that one.
Okay, yeah, this is something that I think a lot of people have mistakenly assumed that they can use. And let's back up. So what is a series rating? So a series rating is where we've taken a circuit breaker and we've tested that circuit breaker above its marked interrupting rating, either being protected by a current limiting fuse or perhaps a circuit breaker. The use of series ratings has been discussed at the UL 5088 Technical Committee called the STP, the Standards Technical Panel, and that was recently discussed, and the idea is that we do not allow the use of series ratings in industrial control panels, and there's a variety of reasons for that. The first one is that series ratings are really intended for panel boards and switchboards, and often the best place to apply a series rating is a lighting panel, a panel that does not have motor load, because there are limitations in the code that limit the amount of motor load you can have when applying series ratings. So in general, we've always taken the approach that series ratings are not permitted to be used in industrial control panels for the reasons I just discussed.
Thank you, Dan. Let's squeeze in one more question. This is the last question. I've been told in some cases the Sccr of the main fuse or circuit breaker in a panel can be used as the overall Sccr for the panel. Is this correct?
I'll take that one, Dan. This used to be a common practice before we had requirements for short circuit current ratings on panels, whether this was part of the UL 508A standard or the National Electrical Code, and that's really not going back too far. I think it was 2006 when the requirements went into 508A for short circuit current ratings for panels. So prior to that, what field inspectors were doing, AHJs, they were basically looking in the panel and finding the maximum short circuit current rating or interrupting rating of the main overcurrent protective device, fuse or circuit breaker, and they were using that as the short circuit current rating for an industrial control panel, and obviously that could cause problems because the equipment that's being supplied by that main overcurrent protective device may not have short circuit current ratings individually as components, in other words, be adequately protected by that main overcurrent protective device. So that's the practice that was employed many years ago, and I think in some cases it may still be happening, especially if there's a panel that's not listed, doesn't have a short circuit current rating on it. But that's what I know it has been done in the past. Dan, would you like to add to that?
Yeah, I think that you've hit it right on the head, John. I mean, it's a lack of information. The whole point of our presentation is show you that, as you mentioned, it's the weak link approach. It's not just the main overcurrent device.
Excellent. Thank you both, John and Dan. This concludes today's webcast. Please look for an email next week with a link to the recording of this webcast. If you're interested in joining us for our next two, please be sure to register via the link provided in that follow-up email. On behalf of both UL and Busman, thank you so much for your time. Have a wonderful rest of your day.